Okay, so we have seen that a Taylor series, for a function which is analytic about some point is convergent in some circle of convergence. So when mod of z minus z naught is less than a certain radius, then it's going to be convergent, and a Lorentz series typically is convergent outside some circle and within another external circle. So it's in an annular region that typically a Lorentz series is going to be convergent. So in this lecture, we will see that whenever a series of this kind is convergent, in fact, we have seen already that there is uniform convergence. They are not only convergent, but they are actually uniformly convergent, which means that they represent functions which are continuous, and in fact, one can argue that they are analytic, and therefore you can take derivatives and you can do integrations of these functions represented by these series. And in this lecture, we will show that in fact we can change the order of integration and summation, right? And so uniform convergence, which we have discussed earlier, has very important consequences which we will be discussing in this lecture. Okay, so let's formally state these two important results. One is about differentiation and the other is about contour integration. So you have a Taylor series of this form, and so you associate this series with some function s of z, and you're given that it converges within the circle of convergence mod of z minus z naught is less than r, then it's completely legitimate to talk of the derivative of this function. And in fact, the derivative of this function has exactly the same circle of convergence as the function s of z itself, and its derivative is also the series corresponding to this derivative is in fact obtained by taking a term by term differentiation of this series expansion. So this is a consequence of uniform convergence, right? So the series not only convergence inside the region of convergence, which is given by the circle of convergence, but also converges uniformly. Therefore, you can take the derivative and then you can do it term by term, and therefore you get s prime of z is just simply summation over n going from 1 to infinity, n times a n times z minus z naught the whole power n minus 1. And again, if you have some contour that lies entirely within the circle of convergence and you're given some function g of z that is continuous, you can multiply this s of z by this coefficient function g of z, and on this contour you take this integral and you have the liberty to change these the order of the summation and the integration. So you can actually do term by term contour integration and then take the summation, and then that also is going to be guaranteed to converge. Let's look at an example, right? So it's best understood with the help of a few examples. So suppose we have, we take the contour to be this unit circle mod z equal to 1 and oriented in the anti-clockwise direction. And suppose we take for simplicity as function like f of z is equal to 1 over z minus 3. So we know that z equal to 3 is a singularity. So f of z is analytic everywhere other than at z equal to 3, and specifically f of z is analytic on and within the contour that we have chosen, which is the unit circle mod z equal to 1. So from Cauchy's theorem, we already know that this integral over this particular contour for this function 1 over z minus 3d is actually 0. But on the other hand, we can actually expand this 1 over z minus 3 as, you can pull out this 3 from the denominator. So you have 1 over 3 times 1 minus 1 over 3 times z minus z by 3 minus 1. So there is perhaps a sign that we should take care of. So I have said 1 over, I'm pulling out a 3, so it should be z over 3 minus 1. So in fact it should be minus. It doesn't matter. So in the end it's just going to go to 0 in any case. So there is a minus, overall minus sign, but in the end, so let me pull out this minus sign. So we get minus of this, and so that minus sign in any case will come out. And then you have a contour integral of this infinite series, but which can actually be written as the summation over all these different contour integrals. And then we use Cauchy's theorem, which is evidently each of these terms has to be 0, right? Because it's a closed contour, and these are very simple functions z to the n, they are all analytic within this region, and for sure it is 0. So in some sense this is a trivial example because we could have directly argued that this contour integral must be 0, but this is just to illustrate how term by term contour integration is allowed. So let's look at another example. So here it's about taking derivatives, right? So suppose you look at the function f of z equal to sine of z. We already worked out its Taylor series expansion. It's simply given by summation over n minus 1 to the whole power n, z to the 2n plus 1 divided by 2n plus 1 the whole factorial mod z less than infinity. So if we differentiate this term by term, so you get a 2n plus 1 z to 2n, and then 2n plus 1 will cancel with 2n plus 1 in the denominator, and then you get z to the 2n divided by 2n the whole factorial, and of course minus 1 to the n stays as it is. And but what is the derivative of this function? The derivative sine of z we have seen is just cos of z from the definition of sine of z, and we also obtained the Taylor expansion of cos of z from first principles, and in fact that is nothing but this expansion. So you see that indeed it is legitimate to differentiate term by term as long as you are within the region of convergence. So if you have a Taylor series expansion for an analytic function and it's convergent in some region of convergence, then you have the liberty to take the derivative of this function and then take the derivative of the series expansion term by term, and that will correspond to the series expansion for the derivative. So an immediate consequence of this freedom to take term by term integrals is the uniqueness of series representations, right? So if you find some series, you don't know that, you don't start with a function and then work out the series corresponding to it. So if you find a series and then you find that it converges to f of z within some circle of convergence, then it is guaranteed to be the Taylor series expansion of f of z in powers of z minus z naught. You cannot have two different series which converges to the same point, right? So the way to argue for this is to simply define this, take this f of z to be this, and then divide by z minus z naught to a suitable power, and then take a contour integral. So, and then on the right hand side you're going to get, there's a contour integral over a summation, but then the earlier theorem tells us that you can exchange the summation and the contour integral, and then when the contour integral will go inside, it's going to allow only one of these terms to survive, and that's going to extract for you the coefficient, and the expression for that is going to be exactly that which is which you would get from the Taylor series expansion. And the same kind of argument will also hold for the Laurent expansion as well, right? So the Laurent expansion, we have seen these coefficients cn's can be written also in terms of the overall function. So again, think of this as representing a function f of z, and then you have to take f of z and divide by z minus z naught to an appropriate power. So ultimately all of these results go back to the fact that the contour integral of 1 over z dz about the origin is 2 pi I, but the contour integral of any other function z to any other power z to the n dz doesn't matter whether n is a positive integer or a negative integer other than minus 1. So 1 over z alone is special, and that will give you a constant 2 pi I. So it's really the same result, and the fact that you can exchange contour integral and summation. So because of this, you can directly argue that for any function which is analytic, if you're looking at a Taylor series expansion, or if you're looking at a Laurent series expansion, the expansion is about a point of non-analyticity or centered around a region of non-analyticity, and the expansion is unique for that particular point and for that region of interest. Okay, so that's all for this lecture. Thank you.